Hello children, welcome to your chemistry online class. Last class we have discussed about a very important gas law called Boyle's law. We'll move to the next law. Observe these two pictures. What are you identifying? Here balloons inside the room, here balloons outside the room in the snow. So what is the difference between the inside the room and outside the room in the snow time? There will be temperature difference, isn't it? And what happens in the temperature difference for these balloons? Observe these balloons. Inside the room, the temperature will high. The balloon will be in the normal size with a normal volume. And if we are moving to the outer, that is outside, there will be cool. So, what is happening? The temperature will be low. The volume is low. Do you know which law is behind this? And we'll see some more examples. In the cold environment, the balloons shrink, and the bright sunlight, the inner tube swells up, and in cold weather, our human lungs capacity will decreases. And in cold time or snow time or winter season, the athletes cannot perform well, and jogging and all the things will be very difficult. Why is this happening? Do you know which law is behind this? Yes, there's a very important law called Charles' law behind this. What is the definition of Charles' law? State that at constant pressure, the temperature will directly proportional to the volume. That we can represent by the equation V proportional to T. That is, volume increases, temperature also increases. Volume decreases, temperature also decreases. Or, if we change this proportionality, we will multiply it with the constant, that is K. And we can also represent it as V1 T1 is equal to V2 T2. We'll see the graphical representation. We'll see the Charles law by FET simulation. Here we know in Charles law pressure remains constant. So we'll see if we are here, you can see the temperature, here you can see the volume of particles. We know in a gas particles always move. So we'll see if we increase the temperature, what will happen? So we'll increase the temperature. So it's expanding. So if the temperature increases, volume also increases. We'll see if temperature decreases. If we are cooling this, what will happen? If temperature decreasing, volume also decreasing. This is the statement of Charles law. If temperature increases, volume also increases, pressure remains constant. If temperature decreases, volume decreases. That is, volume is directly proportional to temperature. This is the representation of Charles law. It is the graphical representation of Charles law. As the temperature increases, the volume also increases, because the movement of that we have seen in the FET simulation, the movement of particles will increases, thus the volume also increases. So temperature increases, volume also increases, pressure remains constant. In this graph, pressure is constant, hence this graph is known as isobar. In Boyle's law, we have seen that their temperature is constant, so it is known as isotherm. If pressure is constant, we can call it as isobar. If volume is constant, we can call it as isochore. And if you see this graph, you can see various constant pressures and various graph. In each pressure, what will be the variation in each graph? So here P1 greater than, P2 greater than, P3 greater than, P4. And as temperature, we'll check first graph. As temperature increases, the volume increases. But in the range minus 273.15, you can see some dotted line. What is this? This temperature in this area, this minus 273.15 degrees centigrade, the volume is nearly equal to 0 degree. This area of temperature is known as absolute zero. Absolute zero is the lowest possible temperature, and something at this temperature has the lowest possible internal energy. It is the very lowest temperature a matter can show the lowest internal energy. This is also known as 0 Kelvin. That is, we know 273 Kelvin is 0 degree centigrade. 273.15 degrees centigrade is 0 Kelvin. So it is known as absolute zero. The volume of the gas will be zero in this case. We'll see a problem based on Charles' law. A sample of helium has a volume of 500 centimeter cube at 100 degrees centigrade. Calculate the temperature at which volume will become 260 centimeter cube. Assume the pressure is constant. How we can solve this? What all these things are given in the problem? We have to keep in mind that if we are doing the problems in the Charles law, the centigrade should be changed to Kelvin. We'll see the problem and how to solve this problem. In the problem, what are the things are given? We know the pressure is remains constant. So hence, we have to apply the Charles law equation. So what are the things given? So given volume is given, initial volume, that is 500 centimeter cube. So V1 is equal to 500 centimeter cube. Then another thing is T1. The first temperature is T1, that is 100 degrees centigrade. So doing problems in Charles law, we have to keep in mind that we have to convert the centigrade to Kelvin. How to convert the centigrade to Kelvin? We have to add 273 to this. So 100 plus 273 will get 373. So the temperature 100 degrees centigrade will be 373 Kelvin. So T1 is equal to 373 Kelvin. So in this problem, we know that the temperature at which the volume will become 260 centimeter cube. We have to find out the final temperature. Here, the final volume is given. We have to identify the final temperature. Final volume given as V2 is 260 centimeter cube. So we have to identify the T2. So how to calculate it? So what are things are given? V1, T1, V2, T2. We know the equation of Charles law, that is V1 by T1 is equal to V2 by T2. This is the mathematical representation of Charles law. So we have to cross multiply the equation. So V1 into T2 is equal to V2 into T1. And we have to substitute the given values. V1 is 500. So 500 into T2. We don't know T2. We have to identify T2. So 500 into T2 is equal to V2. 260 into T1 is 373 Kelvin. We have to identify T2. Hence, the 500 will come to this side. So we'll get T2 is equal to 260 into 373 divided by 500. If we calculate this, we will get the value. So, if we calculate the value, we will get 194 Kelvin. Similarly, all the problems we can do according to Charles law. Another important gas law is Gay-Lussac's law. Gay-Lussac law is a gas law which states that the pressure exerted by gas varies directly with the absolute temperature of the gas. That is, the pressure is directly proportional to the temperature of the gas. And the volume and the mass of the substance or gas remains constant. It is formulated by the French chemist Joseph Gay-Lussac. So we'll see that here we know pressure is varies with temperature. So pressure is directly proportional to temperature. And if we change the proportionality constant, we'll get P is equal to KT. And if we move the T to this side, we'll get P by T is equal to K. Where P is the pressure exerted by the gas, T is the absolute temperature of the gas, K is a constant. We'll see Gay-Lussac law. Here we know volume and number of particles are constant. We'll see what will happen if temperature increases. You can see temperature here and the variation of pressure here. So here now temperature is 300 Kelvin and pressure is 17.5 atmospheric pressure. So I am going to increase the temperature. That is, you can see the temperature is increasing in the thermometer. So temperature increases as, so pressure also increasing. And if you check here, but number of particles are constant, volume is constant. We'll see if temperature is decreases, what will happen? Yes, temperature is decreasing. In order to that, the pressure also increases. So Gay-Lussac's law states that at constant volume and number of moles, the temperature is directly proportional to the pressure. This is Gay-Lussac's law. As we seen in the Charles law, Gay-Lussac's law implies that the ratio of the initial pressure and temperature is equal to the ratio of the final pressure and temperature of a gas fixed kept at constant volume. So this formula similar to the Charles law, we can see P1 by T1 is equal to P2 by T2, whereas P1 is the initial pressure, T1 is the initial volume, P2 is the initial final pressure, T2 is the final temperature. This is the graphical representation of Gay-Lussac's law. Pressure directly proportional to the absolute temperature. We'll see one problem. At a temperature of 300 Kelvin, the pressure of the gas in a deodorant can is 3 atmospheric pressure. Calculate the pressure of the gas when it is heated to 900 Kelvin. Here, initial temperature is given, initial pressure is given. What will be the variation in the pressure at 900 Kelvin? So, final temperature is given. We have to calculate the final pressure. So, P1 is given, that is 3 atmospheric pressure. T1 is given 300 Kelvin. T2 is given. We know the formula, so we can apply this. So, P1 T1 is equal to P2 T2. So, from that P2 is equal to P1 T2 by T1. If you apply all these things, we will get the pressure, that is 9 atmospheric pressure. This is all about Charles law and Gay-Lussac's law. They are very similar and it's very easy.